All right, so welcome back. I hope you guys had a good small break, got a chance to step back, relax for a moment before your calm before the storm here. I know your next like 10, 11 days will be pretty intense, so hopefully you have a chance to recoup for a moment. Task 4, it did not go as well as I hoped. The average was like, I went to like almost a 68, which was like substantially lower than the previous 3 exams. So that was kind of sad. But the good news is you still have the corrections will open up this afternoon. And you can make any of those if you want to make. Just something to pay attention to. There was like a couple questions that have now been repeated through the exams, and it seems like people keep getting it wrong test after test after test. I would look and see any questions that have shown up in the last couple exams, because if I'm putting them back on again, that means they're going to show up again in less than a week. Maybe for you guys it's like next Wednesday, but they'll show up maybe next Wednesday. So I would start looking over some of those things. Look over, make sure that when you are just making the corrections, you're not just doing it to get points back, but you're trying to actually look at what didn't you see the first time, right? So let's try to do work on. I would look at that too. All right. So where are we at for the next couple days? So today we're going to do one lecture on Bernoulli's principle, which is related to how fluids flow when there's no viscosity. Then on Wednesday and Friday, we'll just talk about the final exam. So if there's things that come up while we're talking about the final, you can ask them. Right now, if you do have a question about the final, you can ask and I will answer it in case there's someone who's like, oh, I have this itching question I have to ask about the final. Okay. Then let's talk about Bernoulli's principle. So here, if you didn't know, like this is kind of related. This is Bernoulli's principle and PHYS250. I think that's how it pronounces PHYS250. It's French. But those two are involved with how fluids move with and without viscosity. So this is kind of where we're at in the book is 13.4 and 5. And here's some other videos that you can watch if you wanted to. I'm going to come back to this video in a second. Because first I want to talk about this concept of laminar flow. So laminar flow is when a fluid moves, you can think about like the fluid having these lines that indicate the direction of flow. And so when we have these flow lines, in laminar flow, they all kind of flow together. There isn't any separation to them, or as my picture up top shows, even if they come across some object, they gently flow over them together, and then they come back together and continue about their merry business. So laminar flow is nice, smooth, steady flow. A good example that I can think of with this is if you've ever been to the water park, and then they have the lazy inner tube ride where you just kind of plop into the inner tube, lay there, you can close your eyes, relax, and the inner tube will just slowly drag you down the river. And there's really nothing exciting that happens, and that's why people go on it. Because it's very calm and relaxing. That's like laminar flow. It's very nice, smooth, steady flow. Nothing going on. The other one is called turbulent flow. And this one is when there's disruptions to the flow pattern. Here, this object that's in the middle is causing a disruption. You can see the flow is not continuous and smooth. That is called turbulent. Matter of fact, if you form these extra little swirls in here, those are called eddies. And turbulent flow is more like whitewater rafting. Right? So in whitewater rafting, the rocks and substructures of the riverbed cause turbulence and chaos to the water, and they churn up the water, and it is not smooth and steady. if you've ever been whitewater rafting on a rough day. So this is the idea of turbulence versus laminar. We're going to look at laminar. Now, the other part that I want to mention is we will deal with what we call an incompressible, which means the fluid can't be compressed, and it's non-viscous. So we won't deal with the viscous fluid. Now let's go up and see if I can get this video to work. All right, hopefully.
Right. Okay, so that's pulling it through. Should we be able to see it yet?
Yeah, you can already see it.
You can already see. Oh, what the heck? You sure can. Look at that.
All right, so what I want to point out here, let me turn off this light. You can see, let me see if there's a better stream pattern.
That's cool. Look at that. Okay.
That's pretty good. So you can see that you can see the smoke lines. Those are the stream lines showing you how the fluid is moving. And then you can see when it hits this circle thing, there's a disruption to it, but it's not very turbulent. It kind of moves around the obstruction and continues on its flow. Now there's a little bit, if you see the mouse, there's a little bit of disruption right here, but it's not too bad. Now, later on, let's see, there's some more turbulence. There's now, I'll hold back. Let's see if we can get this out. You can see here, that's really hard to see. Oh, there you go. You can see there that the streamlines are completely obstructed on that block, right? On the back side of the block here, notice the swirling and the brokenness of the lines. The block is disrupting the flow, right? And you can think about this as being, hey, back in the 1920s and stuff, when we built cars, we took a block and we added another block to it, and we made blocky looking cars. They were not very aerodynamic. Now we don't build with block on block, we put curve onto the car so the air moves around the car. Matter of fact, they used to make all those fancy commercials where they would show the streamlines moving around the car to prove to you how aerodynamic the car was. And how that they engineered these things so great. But the idea is that this is what we will look at. We will look at this we will treat our fluids as laminar. Is everyone good with that? And this, in case you were wondering, this girl got the plans for this from NASA. So if you need a family activity over Christmas, you can build one of these, and then you have your own little mini wind tunnel. You can, like I said, if the plans are on NASA, you can get it, and then you can make it. Right? They're not difficult to make. Well, they might be different. You might need some machine tools to make it, but I think it's something you can do. Okay. So one thing to keep in mind is the Reynolds number. It shows up again here. If you forgot, we talked about the Reynolds number in chapter 5. And for us, the Reynolds number, if it's over 2,000, you don't worry about viscosity at all. But if it's below 1,500, you might want to worry about viscosity. All right? And we won't deal with anything that has viscosity with this lecture or on the final. The final will only have what we talk about today. All right? So viscosity of Passai's law is not on the final. Okay? But just remember that that is how you would, if you were ever having to decide, oh, I want to calculate this, that's how you do it. So usually anything, just anything related to blood, you have to worry about viscosity because blood is a viscous material and it sticks to things, it clumps. So especially if you have those platelets and they get stuck in your arteries, they change the shape of the artery and that causes other problems. So yeah, that's why you worry about. Anyway, so what we want to do first, before we talk about how other fluid things, we want to introduce the concept called continuity. So whenever a fluid moves, we have what we call continuity of flow. A continuity of flow is essentially a result of mass conservation, that mass is conserved. And so my picture there, what I'm trying to indicate is we're going to have, let's say you have like a liquid moving through this tube, and then your tubing switched size. So you go from like one size tubing to another, and let's say it was a uniform connection between the tubing. What we want to look at is how does the water or the fluid change as it's moving through these different tubings. So what we're going to do is here's tube 1, and what I'm going to do is I'm going to, as I call it, I'm going to make a chunk of water. Right? So I'm going to chunkify my water. And my little chunk of water has a given volume. It's got an area here, a cross-sectional area, and this is pi, and we'll call this R1 squared. So this has some radius R1. And then it has some length, delta L1. So it's got a length and a cross-sectional area, so it has volume 1 is equal to area 1 times delta L1, length 1. Or I'm going to label these, my volumes will get this weird looking V to distinguish them from velocities. Otherwise I'd have V's running around on the board and they would look the same. So this is volume 1 is A1 delta L1. That's our volume of this chunk of fluid. Now the idea is that the chunk is going to move along down the tube because the chunk in front of it moves and this chunk moves in to fill behind it. And so we can also think about this delta L in terms of the speed at which the chunk moves, because we remember that velocity is just distance over time. So it would be delta L1 over t. So V1 is delta L1 over t, or we can also think about delta L1 as being equivalent to the velocity at which the chunk moves times the time. So it takes a certain amount of time for the chunk to move along down the thing based on its speed. It covers a certain delta L. Now when this tube expands up a little bit and the tube changes shape, what ends up happening is the volume has to be conserved. And this is a very dramatic change, but this is now area 2, which would be pi R2 squared, right? That cross-sectional area got bigger this way. And so when this gets bigger, the delta L2 needs to get smaller this way to conserve volume. So volume, well, this is volume 1, sorry. And so volume 2 under the same arguments would be area 2 times delta L2. Or we see that volume 2 is equal to A2 delta L2. And because mass is conserved, the idea would then be that volume 1 has to equal volume 2 because mass is conserved. As the chunk of mass moves along, it has to be a conserved quantity. So this allows us to say A1 delta L1 equals A2 delta L2. But we can replace delta L with V1T. So we see that A1 V1T equals A2 V2T. Or because the time that we would look at for each chunk would be the same, the time, this would allow us to say A1 V1 equals A2 V2. And that's called the continuity equation for fluids. Is everyone okay with this idea? Now, you've probably seen this before in your daily life. How many people have ever played with a garden hose outside? Right? And then you've either had a sibling or a friend and you say, boy, I really wish I could spray that person over there with water out of my hose. And it's just a regular hose, you know, you don't have any like nozzle on it. The water's just falling out of the hose. So how do you spray somebody over there if you're holding the hose over here? You cover the part of the hose. And in doing so, you change this area, you change the speed, right? And so this is the continuity equation in action, right? Because you've changed the area, you change the velocity of the water. Now, another good, I don't know if it's a good example, but it's an example. For anybody who's enjoyed taking chemistry up on those high floors at the other end of the building, they have these terrible things on the sinks. They look something like this. Right? And if you've ever you turn one on and the water shoots out at high speed and then like bounces back up out of the sink and covers everything around you. And you're like, then you immediately turn it off and you got to find paper towels and clean up the area around you and anything that got wet. And the idea is that really the water, if this wasn't here, the water would still come out at some speed. But this, by tapering the nozzle, increases the velocity at which the water comes out. The volume of water that comes out is the same. It's that taper increases the speed, right? So the idea is that if you ever have time because you're waiting for your experiment to finish, get a beaker, time how long it takes to fill up the beaker, then time how long it takes to fill up the beaker with the nozzle. The time should be almost the same. Right? Now, the only annoying thing is you can't turn it up too high because then the water will hit the beaker and bounce out, and it would be hard to collect the water. But you might be able to try and do that. But this is the idea. By changing the shape of the nozzle, you've changed the speed. All right? But this is just a result of continuity. When the area changes, the velocity changes. Okay? Is everyone all right with that? And this is an overlying principle. Area 1, volume 1 equals velocity 1 equals area 2, velocity 2. All right. Now there is another thing related to fluid, and that's called the flow rate, the fluid movement. And this, our flow rate, for us, now don't confuse this with heat. This is flow rate. Flow rate Q is volume over time. It's a rate, right? Cubic meters per second, milliliters per day. It's a rate of volume. It's a volume change per unit time, right? A lot of times this is, like when they set up a chemical drip, like if you're in the hospital and they're setting a drip for you for whatever reason, they do that based on this. How many like micrograms or whatever per hour or whatever do you need? They set that's a flow rate through the tube, right? And those are usually gravity fed. But that's a flow rate, volume per time. Now, the one thing I always like to mention to the one way to think about this is in terms of air handling. People never think about this, but it's a very important thing. You have an air conditioning unit that has a fan that moves a certain amount of air into the room, and you have to be able to get rid of a certain amount of air at the same time. So you want to push fresh air in and have bad air exit, right? Because for some reason people like fresh, clean air, not stale, old air. Right, it's one of those things. So people, when they build buildings, you have to think about the size of the system, and the HVAC system, the air handling system that your building needs, based on the room and occupancy and all these different things, because you have to have a certain flow rate of air into the area to keep the system working correctly. Now, for us, because we said that volume is A1VT, AVT. If we plug that in, we see that Q is area, velocity, and time over time. So Q can also be AV, right? So that is a flow rate because we've accounted for the time already. But the idea is it's a volume per time, right? Now, one that's not volume per time, but it's a funny one I always think about. It's like toilets have how many gallons per flush? It's the same idea. It's like an event per time, per unit activity, right? If you're ever bored, you can notice on the toilet, they'll tell you, oh, it's like 2 liters per flush or something like that. 1.5 gallons per flush. And they're an environmentally safe toilet. All right, but the idea is these are flow rates, amount of volume per unit time. We'll worry about that later. Now, what we want to think about is what causes fluids to move in a certain way that they move. And to do that, we'll think about our tube again. And we have our chunk of fluid here, sitting here in the tube. We have our little chunk, and the chunk, if we're thinking about this, it has some kind of force pushing it behind. So like if you're standing in a line, and there's a bunch of people pushing you from the backside, then you bump into the person in front of you. So there's forces on both sides of you as you're standing in the mob or the line, and people are pushing you forward or pushing, and like you're just trying to figure out which way to go because you're getting pushed from both sides. And so when we think about that, we can think about the net force is equal to F1 minus F2. Because there's a force behind and a force in the front. And we always count this way as positive and that way as negative. So we have F1 minus F2. But for fluids, we said that pressure is force over area, or forces in fluids are pressures times areas. So for us, our force net on the object, our fluid here, is pressure 1 area minus pressure 2 area, or the net force that's on our object is pressure 1 minus pressure 2. And so if the pressure from the backside is bigger than the pressure from the front side, your fluid will move in this direction. It will move in the direction of the pressure difference. But if P2 is larger than P1, your fluid would move the other way. Your fluid moves in the direction of the pressure difference across the system, right? So it moves in the direction from high pressure to low pressure. Is everyone good with that idea? That's how fluids move. High pressure, usually that's the driving part, is in the behind, and then the fluid moves forward. High pressure to low pressure. All right, is everyone okay? So what we want to do then is we want to actually talk then about Bernoulli's principle. Now at the heart of the principle is that wherever the pressure is low, the velocity is high inside the fluid, and wherever the pressure is low, the speed is high, and wherever the pressure is high, the speed is low. They're inversely related. But what we want to do is we want to get to that equation so we can see this for ourselves. So that is the principle, that if the pressure is low, the velocity is high, and when the velocity is low, the pressure is high. That's the backbone of Bernoulli's principle. But we want to put an equation in place to see that that is true. All right, that's our goal. So I'm going to walk over here and we'll take a look. So let's set up. We'll go to the next slide in a second. Yeah, that's fine. So what we're going to do is we're going to set up our system to have some kind of, so a few different changes. So here in our system, we have our chunk of fluid, and here we have some pressure 1, and it's moving at some velocity 1. So we have the fluids at pressure 1, velocity 1, and we'll count this, and we'll just say, hey, you're at some height 1, y1 above the ground. You could be at the ground, but then over here, you're in a different pressure, you have a different pressure, you're moving at a different speed, and you're at a different height. Now what we're going to do is we're going to use energy principles to look at our system. Because what we can remember is that work changes the kinetic energy and the gravitational energy of our system. And there's no elastic energy in the water. So all we have is the work done changes the kinetic energy plus the gravitational energy. And the work, because work is force times distance, the work will be related to the pressure difference across the fluid. Is everyone good with that? Now, this is the setup that we have. So we said to look at this, we'll look at the work done. And we'll have this. Now, I'm not gonna go through all the substitutions, because what will happen is that everyone gets worried about copying down line for line the derivation of this equation, and you'll get lost in the weeds of worrying about the 900 different symbols and labels that go into this. So what we do is the following. The work comes from the pressure difference. So our work is due to any pressure differences. The kinetic energy is related to the velocities, and the gravity is any height changes that may occur. That's where that's going to come from. And here's the equation solved. There we go. You do a bunch of math if you get this, right? And we're not going to worry about the bunch of math. If you want to do the math, you can, sit down with your friends and work through the math. It's fine. It's not bad. It's just it takes a few minutes to write down all the terms and move them around. So what we see is that pressure 1 plus 1/2 rho V1 squared. Now the rho comes from the fact that where we have mass, we substitute density in for mass. And that's one of the ways that areas, like those terms will all cancel out. And then we have rho G Y1. This has to equal pressure 2 plus 1/2 rho V2 squared plus rho G Y2. Right? So that's Bernoulli's equation in its simplest form. Now what I want to do is I want to do the following. I want to, instead of worrying about the height difference, since that's the master equation, just to get a basic understanding, let's assume we take our tube and we lay it on the table and we knock out any height difference. So we're gonna, for just a moment, let's not worry about a height difference. And so if we take out the height difference, we have pressure 1 plus 1/2 rho V1 squared equals pressure 2 plus 1/2 rho V2 squared. Now I'm gonna move P2 over here and this over there. So we have P1 minus P2 equals 1/2 rho V2 squared minus 1/2 rho V1 squared. Okay, now if P1 is larger than P2, this side is positive, negative, or 0? Positive. So if P1 is bigger than P2, this side is positive. The only way this side can be positive is if V2 is bigger than V1. This proves Bernoulli's principle. P1 is bigger than P2. That means V1 is smaller than V2, right? And this is the idea. Wherever the velocity is small, the pressure is high. Wherever the velocity is large, the pressure is high. All right? That's the main takeaway one of the big takeaways out of this equation. Now the other one, if we're thinking about height differences, this comes back to how cities store water. Where do cities typically store their water? In what? Water towers. They put the city name on it with the mascot or something, and it's all nice. And they'll sit like 30, 40 feet up in the air, maybe higher, I don't know. So why is that? Because that height change allows you to have block water speed and pressure at your faucet. Because that 30, 40 foot height change gives you speed and pressure on your faucet. Now the other thing, you can easily check this if you've ever been in a 2-story building, even at your home, the water pressure on the second floor is lower than that on the first. So you'll notice it. Like if you want, take a cup, a known cup of volume or something, measuring cup, turn on your faucet in the kitchen on the ground floor. Time how long it takes to fill up. Go upstairs to the bathroom. As long as you can measure, you see that the flow is about the same, it'll take longer on the second floor unless you have pressurized water. A lot of times, some homes will have these pressure tanks on the second floor to help put extra pressure back into the line. But you'll notice it pressure difference in first to second. Because of that height difference is small from the city water. All right, is everyone okay with that? Even the Romans knew about height changes in water speeds. They built aqueducts. All right, so let's take a look at a sample problem using Bernoulli's principle. So my problem involves using those orange sports buckets that people drink water, either water or some kind of orange mixture out of, right? They usually sit them on the end of the bench, and then people take their cup and they press the button in and the liquid comes out. So that's what we're gonna look at. So if you've ever seen one of those, that's what we're gonna take a look at. So here's the idea. We have our bucket, and here's the spigot that you push the little button in, and the water comes out, or whatever comes out. Now the top of the water, when it's full, let's just say that that's 20 inches above where the fluid comes out. And what we want to know is how fast does the fluid come out down here? So in order to use Bernoulli's equation, we need to pick points, just like when we solve energy problems. So I'm going to say, I'm going to call this V2. Okay, I'm going to call that V2. Now that means I'm going to call the top of the water up here, that'll be my one spot. So how fast is the water moving at the top of the barrel when it's just sitting top of the bucket? It's 0. So we'll call V1 equal to 0. Now Y1 is 20 inches above that. So Y1, we can just determine this by saying, well, it's 20 inches, and we know that there's 2.54 centimeters to an inch, and there's 100 centimeters to a meter, and we can get Y1. Let's convert our inches into centimeters and meters. Okay, so that's our height that's where the water starts. Now, when the water's down here, what is this height? 0. So Y2 is 0. Now, we only have one variable left to figure out. And I'll assume that we can either have the lid off or we have the little hole in the top. And so that hole, or if the lid is off, what is the water at the top exposed to? Air. And air exerts a pressure on things called, even as I know, it's 1 atmosphere, right? The pressure that the air exerts is called an atmospheric pressure, and it's usually 1. Now in physics, we wouldn't use such a convenient number, but in physics, we use, for pressure 1, we would use 101 kilopascals. So I think it's like 101.2, but it's 101 kilopascals. And this is the pressure the atmosphere exerts on the object. Now, 20 inches down here, the atmospheric pressure is still 101 kilopascals. 20 inches isn't enough distance to cause the pressure of the atmosphere to change. So P2 is also 101 kilopascals. And we do have, when we do other problems, we do have to worry about that K and convert it times 10 to the 3. But for now, we'll be okay. So let's write out our equation. We see that we have P1 plus 0 because our fluid isn't moving, plus rho times G times our 0.508. Now this equals P2 plus 1/2 rho V2 squared plus 0. So Bernoulli's equation is essentially solving it. It's like solving an energy problem. So we notice that P1 and P2 are the same. They will cancel out. So now we have rho G times our 0.508 equals 1/2 rho V2 squared. We could plug 1,000 in for water because they told us this is water, but we can just save that and cancel the rho. And we see that V2 is the square root of 2 times 9.8 times our 0.508. So we multiplied the 2 over here, substitute in for gravity.
About 1/6.
All right, thank you. So this is 3.16 meters per second, which is a number and it's interesting. But what I really want to mention is the following, something to think about if you've ever used one of these things before. So V2 is the square root of 2 times 9.8 times Y1. Y1 represents what? How much fluid you have in the bucket. How many people have ever used one of these when the fluid's nearing the bottom? Does it come out fast? No. So as this water level drops, as the fluid level drops, so does the speed. And then eventually you're like trying to tip it up, and you're debating now about just picking it up and pouring it into your cup because you don't want to wait for the dribbling to come out of the thing as you're waiting at the bottom, right? Now, that's why the speed is related to how much fluid you have in. The other thing that you can do that's fun, as long as it's not like the Gatorade one, if it's just water and you have access to more of it, when the container is sitting up here on the counter or the seat or whatever, and it's full, you can press the button and the projectile motion of the fluid will cause it to hit further away because the nozzle speed is high. But as it drains, that thing will move, the fluid will move inwards back towards here until at the end it's dribbling out because the speed is lower and you're not getting as much projectile motion, right? So it's a fun, you could actually, for fun, you could fill up the tank and then measure the distance where the water lands and check if Bernoulli's equation gives the same speed as the projectile motion equation, right, for a given amount. Like, not, but you could, right? See the fun thing, when you're bored. All right, is everyone okay with this problem? We're using it to set up Bernoulli's. Then I have one, we're going to talk a little bit more about this, and then we'll do one other problem. All right, so we said that this is Bernoulli's principle, and we said that where the pressure is low, the speed is high, and where the speed is low, the pressure is high. And this does allow us to explain several different things. The first one that you can think about is this is related to how planes fly. So the airspeed, when over the top of the wing, the air moves faster than underneath the wing. This causes a pressure difference on the wing that causes a lift, what they call a lift force. And that's what pushes the plane up into the air. Now it also depends on a few other factors, but that's one of the main ideas, is that the wing gets lifted up. Matter of fact, this isn't just on airplanes. This is a problem for like Formula One race cars. They get up to enough speed that they actually have things on the car designed to push them back down. They actually reverse the wing concept to prevent the car from flying up into the air because they get up to high enough speeds to get enough lift force on them because they're light enough. But the idea is that this is why planes fly, right? You get that lift force because of the pressure difference across the wing. And that's why planes also need, they have a runway, to build up speed to get enough lift force, and then they can get up into the air. Now you don't need, oh no, I left my piece of paper. Here's a random piece of paper. Alright. See. So the other thing you can do is just, you can prove this on your own. You don't need to have an airplane. You blow over the sheet of paper. The airspeed is high where I blow over the paper. The airspeed is lower down here. There's a pressure difference that pulls the paper up. That's Bernoulli's principle. Now my last like visual example is in terms of cars, right? If you've ever been in a soft top convertible or seen a soft top convertible and been inside of one, they will puff out when you're driving at high speeds because the airspeed around the car is high, the pressure is lower than inside the car, and they will puff out a little bit, right? Those are just some basic examples. Now my last one, is you get to watch me blow dry my hair. Does involve it. But it can't be good for the hair. Probably good for the hair. That's not part of the Alright, so most people, if you've never done this, it's kind of funny. You can of course use air to like levitate like a ping pong, right? Well, you can have it on time. You can always do this. You can't actually go a little bit of it. Why can you tip it at such an angle and still have the ball float? Like it makes sense when it's underneath here, but I was like over here. And how is that possible? It's because of Bernoulli's principle. The airspeed, when you're inside this column of air, the airspeed is high. The airspeed is low out here. That means when the ball tries to fall out, the pressure difference keeps pushing the ball back into the low speed air, right? It's just like a wing. Now what happens is if you keep tilting it, eventually the force vectors don't line up and gravity will win. But as long as you're in the main stream, you have enough pressure difference that you can keep it inside that stream. But now you have something at Christmas. You can say, see, I learned something. All right, so we only have one other problem I want to set up unrelated to this. This one is just more it's a brute force, here's a problem, solve it. But the idea is that this also is related to how pressure gauges work in like an industrial setting type thing, or there's these things that you sometimes use called Venturi tubes. And the idea is that by monitoring the pressure, you can get to the speed, or by knowing the speed, you can get to the pressure. However you want to kind of look at it. It's an either way thing. So if you're in one of those like industrial factory type things, and they have tubing and running, and you see pressure gauges on the walls, that is so they understand that everything is working nominal, right? So suddenly if you're monitoring the pressure of the system and it changes, that means something in the system changed and there may be a problem, right? So knowing the pressure indicates, it's also telling people about the velocity and other factors involved in their factory or whatever. So that is kind of like a useful thing to know how to do. So for my fake problem, we're going to have a tube on the ground floor, and it's going to take something up to a couple floors higher. And what we want to know is, what are we predicting that our pressure gauge should read at the new location when our fluid is moved up? So down here at the base, We have some velocity 1, which is 2 meters per second. They tell us our pressure gauge reading at 1 is 200 kilopascals. But remember that K means 10 to the 3. We have to include that K. Now, later on, our system has changed heights up to here, but at V2, it is now moving at 3 meters per second. Not only did it change height, it sped up a little bit. And we know that Y1 is 0, and Y2, they tell us, is 10 meters. And what they want us to figure out is, what do we expect our pressure gauge reading to be on the 3rd story of the building? So when we're monitoring our system, what do we expect pressure 2 to be over here? So we can set up our Bernoulli's equation, and we'll just assume it's water. So we'll assume that rho is 1,000 kilograms. We'll just use water. So when we look, we see that we have our 200 times 10 to the 3. That's our pascals for pressure 1. Plus, we have 1/2 of 1,000 times our 2 squared. Plus 0 equals mystery number that we're looking for, pressure 2, plus 1/2 of 1,000 times 3 squared plus 1,000 times 9.8 times 10. And then these are just all numbers and we can solve for P2. So this is 200 times 10 to the 3. This is 2,000. This equals P2 plus 4,500 plus 98,000. So when you subtract these two numbers over to here, I think you should get it's 102 minus 2. You should get 99,500. That would be pascals, or 99.5 kilopascals. The idea would be if you're monitoring this, you expect the gauge to read something like this. If the gauge is reading lower than this, then something is weird. If the gauge is reading higher than it, then something else is not. Right. So if the gauge starts reading lower than that, that means the fluid speed is higher, right, than it should be. That might cause a problem further down. And if this number is bigger, then the fluid is smaller, and you might not be getting enough coolant or something where you need it to go. All right. So that's all I have on Wednesday. I'll either see you tomorrow, we'll take a lab final, or I'll see you on Wednesday and we'll talk more. We'll start talking about our final.